Alright, now we get to talk about naming acids. So this was, I know, tough for some of you last year, a lot of you. It's hard to remember how to name the acids. So the key here is thinking about how it would normally end if you didn't have the H on the front of it, okay? So if you're talking about an IDE ending, let me go ahead and enlarge this here. If you're talking about an IDE ending, then you're going to change that to ic acid and put hydro in front, okay? So this chart that you have on here I think is pretty good. If it ends in "ide," like chloride, that's a classic example here, chloride, you put the H in front of it to make it hydrochloric acid, okay? Then you put the hydro and the ic, alright? That's how that works. Here we go. Okay, hydrochloric, hydrobromic is another example if you have bromide, and hydroiodic if you have iodide. Okay, now, if the anion in the acid is ITE, for example, chlorite or hypochlorite, okay, then you're going to put OUS and acid, and you're not going to have the hydro in front of it. Okay, you drop that, so you just put us acid. Okay, so an example here, chlorite becomes chlorus acid. Now if you have hypochlorite, you see how this prefix right here, it stays, okay? Hypochlorite becomes hypochlorous acid, alright? But the reason we have the us acid on here is because of the ite ending on that one as well. So those are the two examples there. If the anion ends in ATE, like chlorate or perchlorate, okay, then you're going to put ic acid on the end instead of the ATE. Okay, so chlorate, when you add the hydrogen, becomes chloric. Okay, and perchlorate, again, you keep the per, that doesn't change, but the ate changes to ic acid. Okay, I should mention, an acid, when we're naming and writing formulas for these, typically we're thinking of acids as things that have hydrogen in the front of them, okay? That's how you're going to be able to identify those, and it's easy to miss, it's easy to forget, oh yeah, there's a hydrogen in the front there, so this is an acid. So you just really got to pay attention to that, okay? Let's see here, let me go ahead and go back to my... I don't know what's happening. This thing needs to be aligned a little bit, I think. Okay, so we're going to go back to a couple examples here and see if we can figure these out. Name the following acids. HCN. Alright, well, again, we need to know our polyatomic ions here to do most of these. That looks like all of these. So CN is 1 minus, and it is cyanide. Okay, so because the ending is IDE, cyanide, then we're going to put the hydro in front, cyanic acid, okay, and the IDE changes into ic acid at the end, so that's how we would write that. B here, HNO3, NO3 is nitrate. Okay, so because that's nitrate, then we're going to call this nitric acid. Just change that 8 ending into ic acid. Okay, C, H2SO4, that's sulfate, so we're going to call that sulfuric acid. Notice I haven't put hydro on the front of either of these last two because they both end in ATE. Okay. And then D here, H2SO3. Okay, so if SO4 is sulfate, SO3 is going to be sulfite. Okay, so we're going to call this sulfurous acid. Okay, that's how we name the acids. Not too difficult. Although it seemed that way last year, I know. Okay, back to this. Come on. There we go. All right, so binary molecular compounds. That's just a tricky way, a fancy way of saying molecular compounds or covalent compounds that just have two things in them. Okay, this is how we're going to name those. So on these we have to use the prefixes because there can be many different combinations. So you need to know all 10 of these prefixes here. They're really not that bad. Most of them I think you know from math. Okay. The ending on the more electronegative element is changed to IDE. And remember, the way you're going to know the most electronegative versus the least electronegative, because I guess we got both. We're talking about both of those up here. Remember that fluorine is the most electronegative atom on the periodic table, okay, and it's high and to the right. So anything that is lower than fluorine is less electronegative than it. Anything that's to the left of fluorine is less electronegative. So lower to the left tends to be less electronegative. Higher and to the right tends to be more electronegative. And that's a good rule of thumb to figure out those electronegativity values. Okay. So we put the prefix on and we change the last one to IDE. Okay, just like we do on the ionic compounds. So examples there, carbon dioxide, because there's two oxygens, carbon tetrachloride. Now notice, we don't say monocarbon dioxide. Okay? You don't have to put the mono on the front of the first one if it's just one. Now you do have to put a prefix if there's more than one of the first atom. Okay? I think we're going to see an example of that in just a second. Okay? If the prefix ends with an O or an A, then a lot of times, just to make it sound a little bit better, we'll drop one of those vowels. So dinitrogen, it should be pentaoxide. We drop the A because that sounds kind of awkward when we say it. So pentoxide is what that becomes. Not a big deal, I don't think, if you forget that, but that's the way it's usually done. Oh, let's go back for a second. Okay, so now let's take a look at this one. This example. Name the following compounds. SO2. And these are easy. They really are. SO2, sulfur. We don't have to put monosulfur. It's just one. And by the way, sulfur and oxygen are on the same side of the periodic table, so this is covalent or molecular. So sulfur dioxide, because there's two of the oxygens. Letter B here is phosphorus pentachloride. And the letter C here is going to be dinitrogen, because there's two of the nitrogens. Trioxide. Okay. Trioxide doesn't really sound that awkward, so we can keep those two vowels together. If you took off the I, it would be troxide, and that would be weird. So you're just going to have to make a judgment call there on dropping the vowel. All right, last thing we got to talk about here just very briefly is organic compounds, and I'm not spending a lot of time here. Organic compounds are compounds containing hydrogen, carbon, and oxygen typically. Okay, definitely carbon and hydrogen for sure. Okay, a lot of times they'll have oxygen and nitrogen in them as well. But carbon is the main compound that is contained in all living things. Okay, and these carbon-hydrogen compounds make up most of, well, all of the organic organisms that live on this earth. Okay, so these are very, very important compounds. And the way this works, we're just going to talk about the simplest hydrocarbons right now, for the most part. Okay, so hydrocarbon, that just means it's hydrogen and carbon. Hydrocarbon. Okay, those are called alkanes. Okay, and alkanes, their names end in ane, A-N-E. Okay, so you can see that methane, ethane, propane. Okay, and I know you guys are familiar with propane. So they only contain single bonds. All right, and again, we're going to talk a lot more about this later. But the first part of their names correspond to the number of carbons. So there's one carbon in this compound, so it's called methane. There's 3 carbons here, so it's called ethane. And there's 3 carbons here, so it's called propane. Now, I know those first 3, actually really the first 4, don't make any sense at all as far as their prefix. You just sort of have to remember this, okay? Now, when you have a functional group, okay, and a functional group basically just means one of these hydrogens that was here gets replaced by something else like an OH group, okay? Now, especially with an OH group, that's going to end in -al. Those are alcohols, okay? And that just means that one of the hydrogens here has been replaced with an OH group instead with a hydroxide, okay? Alcohols end in OL, so that's how you name them. So instead of putting ANE, you put OL, okay? That's as far as we're going to go on that. Let's just do this one sample problem real quick. And like I said, we're not going to talk a lot about organic chemistry right now because we'll cover that in an entire unit later on in the year. But the last sample problem here, assuming the carbon atoms are in a straight line, write a structural formula for pentane. Okay, now remember, structural formulas actually show a little bit about how the atoms are connected to one another. Pentane is, you might be able to guess what pentane is. Pentane is 5. Okay, and that one actually sounds like it's supposed to. Pentane. Pentagon, you know, you guys know that prefix. So that's 5 carbons connected in a chain. 1, 2, 3, 4, 5. Okay. Because it ends in ANE, that means that all it has is carbon and hydrogen, okay? And so we're just going to connect these carbons to a bunch of hydrogens here, okay? And again, I don't really expect you to be able to do this yet. I really want you to get familiar with what an organic compound looks like so that it doesn't scare you later, okay? So there we go. That's what pentane is going to look like. Okay, the molecular formula for pentane means just write the formula the way we would normally write it. Okay, so the way we would normally write this, C5, and then we got to count our hydrogens here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. C5H12. Okay, so that's just a little bit about organic chemistry, a very brief introduction, and we're going to talk more about that in a later unit. That's it for tonight. See you tomorrow in class.